Hello, guys. Welcome back. So very soon we'll start this session. The session will talk about heat resilient cities and indoor environments. For this session, we'll very honored invite 4 speakers. Actually, their topic is quite diverse, from the climate modeling, the private sector innovation, microclimate monitoring, design guidelines, and also the real practical the programs in Melaka. Let me introduce the first speaker. Associate Professor Yuan Chao is currently a tenured associate professor at the Department for Architecture, National University of Singapore. He received the Presidential Young Professorship and also founded the Urban Climate Design Lab at NUS. He's also the principal investigator for many very important design and also climate projects. As an architect, urban climate researcher, and educator, Yuan's teaching and research focus on the climate responsive urban planning and design for sustainable and resilient cities. Currently, he also, in collaboration with MIT ET Zurich, to conduct several studies on urban climate. He also served as a director of research in NUS Cities, associate editor for Urban Climate Journal, and editorial board member as a landscape and urban planning, etc. Currently, he also established an IoT sensing, networking, and integrated ground-based LiDAR into it for the ventilation of the both micro-scale and meso-scale urban climate models. So the floor is yours. Dr. Yuan, welcome.
Thank you for the introduction, and thank you for having me here. Okay. I'm going to talk about the climate modeling and the measurement. And nowadays, actually, the people living at the tropical cities are facing very high heat risks. In the future, this kind of heat risk will be even more severe and intense because of climate change and urbanizations. I do believe that if we can provide more information to make the climate information more accessible, and if we can teach the people how to appropriately use this kind of information, then we can significantly decrease the risk, and also we can reduce the healthcare cost. So I start from this study. I believe you must be very familiar with this kind of result year by year, air temperature increasing. But this is not the globally averaged impact of climate change on air temperature. This is the local impact of the climate change on air temperature in Singapore. We use the machine learning method to combine the real measurement and the regional scale modeling results. So this red line actually is the air temperature increment in the very near futures in Singapore. Not only climate change, we also have urbanizations. You can see at the different areas, both air temperature are increasing, but with different speed. There's a gap. Singapore is so small. The impact of climate change in Singapore, different areas, should be the same. So this gap actually is caused by the urbanization. And based on the master plan from URA, the planning department, actually we developed a model to estimate. So how much air temperature will be increased in the future only by the urbanizations. So you can see different areas with different urbanizations. The air temperature increment is very different. At the metropolitan areas, because it has been developed already, so the air temperature increment is quite limited, 0.2 degrees. But at north areas, the government is planning to put more public housings over there. So the air temperature increment is quite significant, about 0.8 degrees, almost 1 degree. We are also facing this issue in Singapore caused by the anthropogenic heat, because it's hot every day, right, in tropical areas in Singapore. So most of people need to use the AC almost every day also. You can see this is the very typical street canyons within the public housing areas, the HDB areas. On the facade, we can see a lot of AC condensers. And what the AC will do, remove the heat from the indoor areas to outdoor areas. And the heat at the outdoor areas will increase the air temperature. So after dinner, when you walk with your families at this kind of street canyons, you feel it's very hot, right? So it's not because of climate change. It's because your neighbors are using AC. Yeah, it's because of this kind of designs, okay? So people will be less willing to do exercise with this kind of microclimate. So yeah, it's not very good for the health. This is another even more extreme examples. This is the very nice shop house in Singapore, in Chinatown. Very nice courtyard, the locations, yeah, but nobody wants to stay at this kind of courtyard. The reason is so obvious, right? You can see so many AC condensers, and all the AC condensers are shooting the heat to the people who in this courtyard. So we developed the GIS-based model to estimate what's the impact of the anthropogenic heat on air temperature. So you can see this is the results for two scenarios. Normal scenario with annual wind speed, and the more extreme scenarios, which is actually for the inter-monsoon season. The incoming wind is very low. It's only about 1.1 meter per second at 300 meters above the ground. So near ground areas, almost no airflows. So at this kind of scenarios, actually the impact of anthropogenic heat on air temperature is very significant. You can see, no need to talk about urbanization, no need to talk about the climate change. Only because of the anthropogenic heat, the air temperature within the street canyons will increase maximum 2 degrees, 2.3 degrees, which is very significant to the health, to the energy consumptions, to the well-beings. This is another visualization. We show the dynamics within 24 hours, the impact of the anthropogenic heat on that temperature. So this kind of visualization actually is very helpful to the stakeholders to make the right decisions, okay? What kind of actions they need to take to help the vulnerable peoples to prepare this kind of heat risks. We also conduct the air ventilation assessment work in Singapore. We evaluate what's the impact of the buildings, the roadside trees, on the natural ventilation, because we expect to use the natural ventilation to blow away the heat, to blow away the air pollutant. So even though the Singapore is very flat and very small, but we can see the wind rows at different locations are quite significantly different. And based on the different prevailing directions at different monsoon seasons, we identify the air pass. This is the real government project, and the government want to put a very high dense development at the PLAP areas, and which actually was the airport. So we identified the air pass to try to minimize the negative impact of the new development on the leeward areas, which actually is the East Coast residential areas. So the air pass has been identified based on the 2 monsoon seasons. We can see that the air pass orientation is very consistent with the wind rows, the localized wind rows. Means that actually the air pass are very accurate and it works. We did not choose to give the government the to-do list. We choose to give the government not to-do list. We hope that it's easier to them to follow up. So you can see the 4 the circles here means that actually we don't recommend to put any new development at this kind of areas. If we put the more new development at this kind of areas, actually will significantly affect the natural ventilation performance at the leeward areas. If the government really want to put the new development at this kind of areas, then the very strong mitigation strategies should be applied. Not only modeling, we also do the real field measurement, as Prof. Ren mentioned before. So we set up this very comprehensive measurement network at the CBD areas with the Doppler LiDAR measurement and the weather station near ground measurement. So the Doppler LiDAR, this guys actually is very powerful, can shoot the lasers to the very high level in the atmosphere. This kind of technology was used in the airport, has been used in the airport to measure the wind shear to help the airplane land safely. Now we are using this technology to improve the safety simulation accuracy. Yeah, so we directly use the boundary condition measured by the LiDAR to drive the safety simulation, and the safety simulation results will be much, much more accurate. And yeah. Talk about the resilience, right? And we should not only look at the average situations, we also need to look at the extreme situations. So we conduct this kind of simulation with different boundary conditions. We can see with different incoming wind speed actually the airflow, the heat dispersions are totally different at urban areas. So we conduct this research using NSCC national level supercomputer. Very comprehensive simulation, very high resolution, took us almost 1 month, for this result. And this is another simulation. We look at what's the impact of the different wind directions on the air pollutant dispersions. You can see, based on the average situations, some location is the leeward areas, but at some different scenarios, the leeward areas will be the windward areas, so that there will be the negative impact. This is another study. We also look at the impact of anthropogenic heat, but we look at what's the outdoor anthropogenic heat impact on the indoor air temperature. Because as the architect, as the educator, we always want to encourage the people to open the window, use less AC. But we need to guarantee when the people open the window, it's the fresh and the clean and the cool air, but not the air pollutant and anthropogenic heat from the neighbors. So we want to know if 30% of the residents choose to open the window, for whatever the reason, enjoy the natural ventilation, and what's the impact of the anthropogenic heat from their neighbors on indoor air temperature. So here, actually, good news and the bad news. The good news is that the latest HDB designs, the towel-shaped one, the impact of outdoor anthropogenic heat on the indoor air temperature is not significant, because the towel shape actually is very good for the natural ventilation, outdoor natural ventilation. The heat can be dispersed very fast. But the bad news is that at the old HDB, and with this kind of very deep and long street canyons, and also these two designs with the courtyard. Courtyard is a very nice design for the community. But for the climate, it's not very nice, because the heat cannot be dispersed. So sometimes, even though the natural ventilation is very good, but the natural ventilation actually will carry the heat from the outdoor to the indoor. So we run the CFD simulation very carefully. We see the maximum air temperature increment only caused by the anthropogenic heat from the neighbors. Could be 4 degrees, means that if I choose to open the window, enjoy natural ventilation at nighttime, my neighbors are using AC, the indoor air temperature could be increased 4 degrees, which is horrible, right? Yeah, I cannot sleep, right? Yeah, with this kind of air temperature increment. Not only the climate modeling and the measurement, we also try to see what's the impact of the heat on different things. For example, on health, on energy consumption, and on carbon emissions. So this is the very simple but also very straightforward study. We want to see, okay, which districts actually the heat risks for the elderly is higher. So the method is very simple. This is the map of the UHI intensity, and these two are the map of the elderly distributions. We just overlay these two maps in the APAQ. Then we get this one. This is the heat risk assessment to the elderly. You can see the red color districts. It means that at these districts, the UHI is very intensive and the elderly intensity is very high. Of course, the heat risk is high. So that, okay, based on this map, the government can make the right decisions at which district they should spend more resources to help the elderly to prepare themselves to mitigate and adaptate the climate change and the heat risks. Yeah. And currently, not only the residential areas, we are setting up the network at the hospital campus. This is the campus of Singapore General Hospital. Of course, the people in hospital, they are vulnerable. And we are also setting up the network at the primary school campus, because we also care about the school children. And this is the Doppler LiDAR, which will be installed at the science center, and this is the weather station to measure the near-ground microclimate. So I talk a lot, but at the very beginning, I said that we hope to make the climate information more accessible to different stakeholders. That's the reason why we developed this digital platform, and I prepared the video. You can have a look. Yeah. So we work with the ETH Zurich to develop this platform. So to access the microclimate information, you just need to choose the site. So it's very simple and very straightforward. Then, okay, the platform will tell you what's the UHI intensity at these areas. And we provide both planning index and climate index. And the users is allowed to choose multiple sites to do the cross comparisons. Everything is automatic. The boundary conditions will be also automatically set up. So this is the quantitative cross-comparison result. So the whole thing will be very efficient. And you also can choose different climate features. For example, this one is the urban wind permeability. And you see the wind rows, which is the local wind rows closest to the site. And this is also automatically chosen by the platform. So you don't need to run the CFD simulation. You can easily access the information and to make the right decisions. And this is the solar irradiation, so that you can make the decision like where you should put the vertical greenery and the solar panels at the different surface. Not only at the neighborhood scale, and we also provide the results and the visualizations at the city scales. Because the visualization is 3D, so it's very straightforward, very easy to the urban planners to identify the air paths, just like what we did in the PLAB project. And this is the impact of the anthropogenic heat on air temperature. And this is the air pollutant dispersion. So different color means that different dispersion potentials of the air pollutant. And the urban planners and designers are also allowed to input their own design and the plannings into this digital platform. Almost done. Yeah, thanks. Yeah, so the designers can see what's the impact of their designs on microclimate. Yeah, so it will be very useful at the early stage of the design. And this is the application in Zurich. Currently, both NUS and ETH Zurich are using this digital platform in their design studio teaching. Okay, I think I just stopped this here. Okay, and this is the QR code. You scan this QR code, you can access the digital platform. Yeah, this is the open access, totally free. Yeah, thank you very much.
Thank you. Please have a seat first. Okay, thanks for Dr. Yuan's very impressive, informative presentation. Now we move to the next speaker, Mr. Joseph Deng. Currently, he is a head of business development at APAQ Group, an environmental engineering consultancy firm incorporated in Singapore, where he leads the partnership and market development in the Southeast Asian, with a background in civil engineering, environmental engineering, and also master degree in environmental management from the NUS. Mr. Deng has both government and private sector working experience on a wide range of environmental projects spanning air quality, climate change adaptation, water-sensitive design, groundwater, soil remediation, industry emission, and pollution control system. Now the floor is yours. Let's welcome Mr. Deng. Thank you.
Right, thank you, Prof. Ren. Thank you, everyone. I'm glad to be here today, and as a NUS alumni, also to support NUS, the inaugural forum of Southeast Asia on heat. And yeah, I'll share my view and perspective from a private sector practitioner's view, and I hope that I have equally attractive visualization and simulation like Prof. Yuan, but unfortunately I don't. So I'll keep my presentation a bit more concise. So first, a quick word about our company. So we were incorporated in Singapore since 2013, and we pride ourselves as one of the first environmental engineering and specialist company that really look into the area of environmental monitoring and instrumentation equipment. And then since 2024, since last year, we become part of the NVIDIA Global Environmental Technology Group, and we cover a very big, diverse, complex, and growing market of Southeast Asia, Australia, and New Zealand for them. So our area of work, as I have mentioned, we initially started off with a mission to bring technology to this very diverse, growing market, and we come from an environmental engineering background, so naturally we serve the heavy industries in terms of all the air quality, pollution, emission, and all that. And interestingly, I would say that climate and meteorology is a unintentional field that we have ventured into, and we have gathered quite a lot of good results because of and thanks to the emphasis in urban climate research that Singapore has been doing over the last decade. And I'll just give a very quick overview of, in terms of the technology for meteorology and climate sensing. And we believe it is a very mature technological field when we talk about meteorology market, right? Supporting the meteorologists, doing reporting, running weather models and all that. And actually, traditionally, companies like us are kind of born out of research programs with scientific authorities. We develop new measurement techniques, right? We test the equipment, we try to calibrate, certify the equipment, and try to bring it to the market. And microclimate, interestingly, is nothing very different to me. In terms of the core technologies, when we all care about temperature, humidity, pressure, wind, rain, and so on and so forth. But then, because of the different markets, in the relationship is quite different. So in the conventional meteorology market, typically the buyers basically are government agencies, scientific authorities, laboratories, and so on. And companies like us, of course, we can develop technologies. We must work through suppliers, distributors, industrial contractors, and to bring it to the market, and then to support the scientific community and researchers. Whereas microclimate, the topic of today's presentation, is I think it's very interesting because it's a very diverse market. And microclimate is really, it's like meteorology, but it's not meteorology because the applications really lie at the intersection of multiple domains and sectors. So it's really very much driven by the use case of different domains. For example, we talk about microclimate, we will ask about how cities will require very localized data for the temperature, humidity, wind, etc. to use it to predict and forecast, for example, the information about traffic impact, tourism, and heat safety, for example. And then, of course, there are different specific needs by building sector in terms of thermal comfort and ventilation, and by agriculture in terms of like soil moisture, solar radiation for photosynthesis and nutrient level and all that. And about environment, of course, the dispersion of air pollutants and so on and so forth. So it's driven by very unique use cases of different sectors. And then as a result, the users tend to not emphasize so much on the accuracy and performance of sensor technologies, but rather how relevant are the other data really in terms of the spatial and temporal qualities to support their decision making and to improve their performance. And that is how we see the microclimate market differ from the conventional meteorology market. And when we talk about buildings, architecture, I think thermal comfort is the very much the focus of building market, because everyone care about the climate change, the impact on the comfort, on the health of the productivity of occupants, and also energy consumption, right, and all that. So we feel that past efforts for the thermal comfort in the building sector were mainly in urban climate research and building design and modeling, like CFD simulation, all that. But then nowadays, with the advancement of indicative sensors and IoT, so-called smart city technologies and all that, there is really a growing interest that we have seen for how to incorporate microclimate data into continuous monitoring, adjustment, and optimization of building performance. And in particular, when we talk about thermal comfort, we need to also integrate like personal data, right? Like metabolic rate, clothing insulation, and to derive various indicators such as UTCI, WBGT, PMV, PPD, PET, etc., for both indoors and outdoors. So that is an area of research that we are actively involved in. And in terms of the scope of microclimate project, I think nowadays people tend to kind of mix everything up together, right? Smart city project, microclimate project, IoT project, and so on. So typically, for us to play in this field, I think as industry player, we need to be familiar with, of course, monitoring technology sensors, but increasingly we need to be really familiar with the communication, data protocols and all that, and then how to ingest data into the database and how to provide a good looking but also valuable user interface to the user to visualize data, to extract data to their own specific applications of the software on the software side. And that is where we need to, of course, get familiarized with all the use case, the domain knowledge that can develop microclimate sensor data into different data analytics solutions. So I will share a few specific projects that we have undertaken in Singapore supporting the various research programs of our government agencies as well as our research institutions to share how we, as a private company, are sometimes willingly, sometimes forced to kind of improve our value and kind of expand our scope of services. So the first one actually is the very famous project in Singapore. Is called the Integrated Environmental Modeler. Back in 2014 to 2017, I think there are a few phases of the project. So basically, we are required to support the A*STAR, the National Research Agency, Institute of High Power Computing, to develop this environmental simulation program supporting the town planning for HDB. And our role is to really help them design the sensor network, deploy the sensor network across the whole half of Singapore in a few phases, and collect like over 2 years of data with over 90% data availability. That is a performance target. And our role, of course, is to ensure that the sensors must perform up to the standard, must be no drift over the entire monitoring duration, and we have to really go around, maintain the sensor, validate the sensor, check if there are any communication errors, and do the data reporting, and make sure that the researchers are confident enough to use our data as a basis to calibrate the model simulations. Yeah, so our role is, I would say, is mainly still focused on the hardware, the whole hardware package for the simulation. And the second project I'm very proud of as an NUS alumni is the NUS Cool Campus Network supporting the School of Design and Engineering. And I think, again, the use case is very unique, is to how to deploy a very dense network of microclimate sensors across the whole of campus and use it to really to push the data almost like a real-time basis to the NUS database and help them to use it to drive the simulations and the digital twin on campus. And that is very similar to Prof. Yuan's work, but on a bigger scale across the island. But only the NUS campus network is much denser, and there are a few very special sensors that they are monitoring the multi-level and can be extended up to 10 meter high in the building canyon to run also the vertical simulation of the thermal, the heat. And another project that we are partnering instead with NUS, with our researchers, is to help HDB, the Housing Development Board, to deploy a network of sensors across the Tampines estate, housing estate, to use it to verify and to prove that the cool painting basically works, right? I think yesterday the URA director, Wen Tong, said that the cool coating can achieve 2 degrees reduction of the heat across the buildings that are coated with cool paint. This is something we are trying to validate, of course. So our role here is the main contractor, and we are gathering all the data, developing our user interface to analyze the data and use the user interface to run different analytics. And then we get our professor in US to help us develop the analytics functions to prove that this indeed can work. And of course, our role as the industry player is to bridge this knowledge, because the agencies will hope that it can achieve 2 degree reduction, even better. But then in practice, everywhere across the building estate is different, right? Surface temperature, the corridors, the indoors, and the outdoors comparison. So there are a lot of different conditions, right? And this is where we come into play to level the knowledge and to try to develop something that's confident for the agencies to roll out and really to scale up across the whole of island. And this is the methodology of the testing, and is basically we use this kind of information provided by the researchers to drive our citing of the sensors and correlation of the data analytics. Yeah. So I will talk a bit about how we see the future of microclimate market will evolve. So firstly, how can companies like us scale diverse solutions, new solutions for the market? And I'll take an example of this WBGT that you heard so many times in this forum. WBGT is a very old school, I would say, very simple, very conventional kind of index, right? And then because of the unique need by our regulators to have continuous outdoor monitoring, we have to tailor the sensors as per the ISO 7243 guidance, and including how it can be continuously operated with very low power consumption, very low maintenance, without any, say, routine maintenance over a couple of months or up to half a year, and that is the performance criteria required by the government. But then the industries, to be honest, that is something we are working on, but without a market standard, they don't care. They can choose anything off the shelf, right? A handheld device, some even simulated data, derived data with indicative low-cost sensors. And that is something we have to, as environmental specialists, we hope to work on to bring the technology development to this market, to get it certified, prove the performance, and then build our value add in terms of user-relevant data analytics of safety and productivity improvement, and to offer an integrated solution. And several emerging use cases that we have worked on, and also supporting the research institutions and market leaders such as our CERES, our Solar Research Institute, and also Kajima in Singapore, is we have seen, of course, everyone understand the importance of net zero, driving towards net zero, and building sector really play a huge role in this market. And then currently, all the efforts looking at how to improve buildings to super low energy building through all the smart FM, energy efficiency, but eventually how do we move beyond even super low energy building towards net zero building or even energy positive building. We've seen some emerging trends, right? Like building integrated photovoltaics, like mixed mode ventilation, biophilic design. And there are specific needs for microclimate data to be integrated into the building energy monitoring system as continuous monitoring, optimization, and adjustment. And this is where we see our opportunities to develop certain solutions for this region, tropical region. So I'll quickly wrap up. What are the key takeaways I would like to share? First, microclimate data applications exist at the intersection of different sectors. And second, there are a lot of emerging use cases and use cases very specific to our tropical, high-density urban environment, and they require very different business model and approaches to innovation compared to the conventional environmental technology or meteorology market. And third is private sector and researchers have really complementary roles to scale up solutions. And let me wrap up. I'm really happy to hear a lot this time in this forum that people say that Singapore is really well placed to share the way forward on how to tackle heat. And indeed, there are a lot of research that we consider as groundbreaking in terms of the depth and in terms of the scale, right, in Singapore. But how do we replicate these experiences and really bring the solutions across to the Southeast Asia market? And that is something we hope as building a regional enterprise, a company, that we can step up to also support with our partners across the Southeast Asia. Yeah, thank you so much.
Thank you. Okay, thanks for Mr. Deng's very informative presentation, and let us know more about the practice from the industry sector. Now let's move to the next presentation. Our third speaker is Mr. Lall. Currently, he is a principal of the Lall Architects and Network Changemaker of Global Buildings Performance Network. Before this session, I have a very short conversation with Mr. Lall. He just told me, if you want to introduce me, just mention his work is affordable housing, right? All types of buildings in India. That is very short, but very easily to remember. Actually, apart from that, Mr. Lall also served as a formal dean of the studies in the formal TVB School of Habit Studies in New Delhi, and he also his work are widely published. His firm is currently working on this affordable housing for all architect zones in India. His engagement with academia started in the 1990s with developing curricular teaching method to address sustainable architectures. Now, floor is yours, Mr. Lall. Thank you.
Thank you so much. Thank you very much, and I'd like to thank GHIN for giving Global Buildings Performance Network an opportunity to present the work that they're doing, not in Southeast Asian region, but this time in India, which is closely related, and in some ways it is very different from the climatic situations in Southeast Asia. And it's interesting to be able to compare and perhaps learn a little bit one from the other as I go through this work of ours. So GBPN has the aim of tackling climate emergency by decarbonizing one of Earth's most significant carbon pollution sources, the building sector. The focus is on the building sector. And this is done by setting up coalitions to make that impact. And this is now, shall I move forward? Yeah, and GBPN is operating in many parts of the globe, as you can see here, and have a big program in India. And I happen to be leading one of the research cum development projects in India at the moment, devoted to affordable housing. So it's healthy and climate resilient affordable housing. This project is based on a series of research done with a number of co-partners in this research work to arrive at recommendations to upgrade our national building code for low-cost housing proactively as we run into climate change, as we run into temperature rise, and as we run into urbanization with high-density development, as we've just been watching. There is a huge demand for affordable housing. In fact, it's going to be the biggest sector of construction in the next 2 decades across the country. The emphasis has so far been on delivering quantities, but it has overlooked the qualitative aspects of affordable housing provision at the state level, at the city level. And climate appropriateness for comfort, resilience to climate change, and holistic health and well-being of residents, I believe, or we believe, has been overlooked so far. Just quantitative. Shelter over your head, that's good enough. But what kind of shelter over your head is the real question over here. India has been experiencing rising temperatures very dramatically. The heat waves have been lasting longer, and the intensity has been going up and up. And you can see there are areas of India where they've seen temperatures above 42 degrees centigrade. Large populations are subjected to that. And most of the population has seen temperatures rising over 40 degrees centigrade. So you can see that the temperature rise in India, in the subcontinent, is of a different order altogether, right? And we're talking about climate change. We're accepting there's going to be at least 2 degrees centigrade rise on average. And that we have to take into account the effect of urban heat island, which will be compounded in the future with anthropogenic heat. At the moment, most people can't afford air conditioning. But when that comes in, it'll get much worse. And then you'll have to say that who are the most affected in our city populations? It's those poor people who can't afford air conditioning. They would be the most affected, even though they're getting new shelters to live in. The tendency is to move towards high-rise, high-density development, Singapore style. And we are not that short of land as you are, sir. We have got plenty of land. But somehow, this formula, this arithmetic formula, especially by a lot of our folk, administrators and politicians, etc., coming here and being impressed by Singapore. They say, the future looks like this. And they feel that's the way they have to go. And I keep warning them, look, you have other choices. It's not necessary to do it that way. So there is a holistic definition of health and well-being, which has been developed by the World Health Organization, and it is to be appropriate now for affordable housing. So what we are really looking at is climate change overlapping with the needs of affordability, how to deal with it at low cost, and how to ensure health and well-being in those homes. I must point out that this is a challenge being faced by many emerging economies that are facing rapid urbanization. We're talking about urban growth. Climate change impacts have many dimensions and call for resilience as well as mitigation strategies. So our challenge is to deal with resilience not only as an adaptive measure, but as you send in your recommendations, within that is built in a potential of mitigation. Lower income groups are the most susceptible to temperature rise, and they cannot resort to cooling technologies. We've been mentioning all these dimensions of health. We've been focusing a lot on physical health. We'll be looking at that here too. But there is also social and psychological health. It's good to see that I've learned in this conference and a few presentations that were made in this hall and the previous the plenary sessions, that psychological and social health are connected to physical health. Dealing with physical well-being, deploying resilience strategies has a lot to do with your psychological well-being. And the nature of housing determines to a certain extent your social and psychological health as well. So very simple things. I mean, now we're into the guidelines. They're very simple things. First things first, we just make the building envelope such that it will resist the heat from coming into the buildings. Protect yourself during the daytime from the heat coming in, and relieve the heat during the evenings and nights by good ventilation. A very simple principle in most warm climates. So optimize the integration of climate responsive passive design strategies and low energy devices to maximize indoor thermal comfort. We have something called, where there's a code, which is called the ENS Performance Standard, and it is at the moment built on historic climatic data. We are suggesting that you should build in the potential of 2 degrees rise in temperature and add another factor for urban heat island effect, and then make them even more resilient, even more protective than what the code presently says. So the code has to undergo substantial improvements. These recommendations have now been made to the Bureau of Energy Efficiency to amend and simplify the modes of calculation. Sometimes these codes are very complicated, as you probably know. If it is affordable housing that's built in small towns by small people all over the country, the way you apply the codes has to be very simple, and it must be simplified. At the moment, there is calculation that has to deal with total building performance in a block of flats or a group of flats, right? Whereas what we really need to do is to isolate each building, each house type, and do a calculation just for that house, very simply, and make sure that it meets your standards. Much simpler to do. Thermal mass, now in the tropics generally, when you don't have much diurnal variation in temperature, you ignore thermal mass as a modifier of temperature indoors. Whereas in India, most of the subcontinent has fairly high diurnal variations. In our standards at the moment, thermal mass has not been incorporated into a consideration. So we've developed standards for incorporating thermal mass as one of the aspects of construction, especially of the external walling and the roofing systems. Ventilation, of course. As you go into dense development, what happens is that the buildings in front of you will block natural flow of air. And as you just pointed out, the type of building design that you do will also impede the flow of natural flows of air. Cross ventilation is extremely important. We are now recommending for the first time that aided cross ventilation should be incorporated into simple home designs. Put an exhaust fan at one at the house, make sure that between rooms that are one behind the other, there is a ventilator through which air can be drawn, so that through the night you can get about 15 air changes per hour and thereby cool down the heat that is developed during the day rapidly inside the home, thereby enabling people to have a restful sleep. A very simple device, but that is what has to be incorporated. We have some codes about external shading, but they're not rigorous enough. They are not really telling you that if you're facing into the rising sun or the setting sun in the afternoon, you've just got to have a device that you can pull down when the sun is striking a window. In fact, our recommendations are that you have to eliminate the sun falling on the glass altogether during certain times of the day, especially taking care of eastern and western orientations. And there are simple ways of doing it, so the new code will propose that. Insulation of the roof has to be improved. The roof gathers the highest incident radiation and therefore needs to be very much protected. Somehow people say that if you look at the total building, performance, you're only looking at, you're not isolating the people under the top floor roof, in the top floor. So that becomes an important consideration. If you incorporate all these strategies, it is very clear, as you can see in this diagram, that you can bring, by incorporating all these process strategies, something closer to possible comfort as you improve the building design. Very simple, that you have to be protected from disease. Fly wire meshes, mosquito meshes in windows are to be now mandated. And you have to have a distance between where the housing is located and the sources of pollution. Looking at social health, when homes are small, and there are quite a few people living there and half of them are children, a lot of space is required immediately outside the home that must be sheltered. So a minimum standard for green space and open space per person is required. That enables, we call it the habitable outdoors, enables people to be more comfortable outdoors, especially the children and the elderly who cannot be cooped up inside the homes. Very important, this is a recommendation, that we think that women who are the homekeepers of the community should have an equal say in the management of their common assets, and also developing culture of resilience within their communities. We say there should be a limit to densities because we believe that high densities produce social attrition, and this is exacerbated during high temperature events, during heat waves, and therefore we are suggesting a limitation of densities and also building heights. There are many misplaced incentives which say that if you do a green building, we'll allow you 2 or 3 more floors. In fact, it's going completely the wrong direction. So let me just move on. If you look at the psychological dimensions, what we are seeing is high-rise, high-density, where there is a real shortage of space and real crowding, as you can see in this image, right? You can see there'll be social stress, there'll be psychological stress. Apart from that, people who are living on the upper floors are feeling very much imprisoned and fear hazards of things like fire or earthquake or even the outage of electricity and water supply. But on the other hand, if you can limit the densities and heights to 4 stories, you will have a much better environment from the point of view of psychological comfort, and of course microclimate itself gets improved in the process. There is a concern for fire safety, and this seems to override everything else, and we think that you have to revisit the requirements for fire safety, where fire tenders have to go all around the buildings, causing hard paving to be formed between buildings, and that in itself increases the urban heat island effect. So if you review that, bring down the building heights, reduce the fire safety requirements, you have a much better microclimate that is produced in the process. This is perhaps the most important thing, risks against resilience. This is, on the left-hand side, is what we are moving towards blindly. On the right-hand side, what is actually really possible in the space that is available in and around our cities. Environments where actually on the rooftop, you could have sufficient PV supply. You can have sufficient PV supply to make 80% of simple living below those floors at 4 to 5 stories height. And that kind of resilience is really something that is really possible, especially when you foresee outages due to floods or due to other outages, electricity supply is disrupted, water supply is disrupted. We have recommended the provision of resilience centers for every 150 dwelling units, and these resilience centers would be shaded, insulated, and have operable mechanical ventilation, and maybe also equipped with air conditioning, and cooling strategies will be provided there. Very important when you run out of water. You must have a store of drinking water available, at least 2 days worth of store of drinking water. Interestingly, what happens is that as we look at the pattern of urban development and pattern of providing for housing in cities in India, there is a relationship between building height and density, resilience, and microclimate, which affects our health. And so we are talking about limiting height, limiting densities. As you look after health, automatically, by reducing the height of the building, you reduce embodied carbon of construction. As you reduce the height of the building, you reduce operational energy in construction. You improve microclimatic conditions. And importantly, integrating solar PV on the rooftop of 4 or 5 story high buildings becomes an urban level possibility. Thank you.
Thank you, Mr. Lall. Okay, let's move to the last presentation. Our speaker is Assistant Professor Perrine Hamel. She's from the Asian School of Environment, Nanyang Technological University, Singapore, and she served as a principal investigator at the Observatory of Singapore and also head of the Resilient Inclusive Cities Lab. Her research examines how urban nature, parks, trees, green roofs, etc., help the cities become more resilient and address the major climate challenges in Southeast Asia. She received the Singapore National Research Foundation Fellowship in 2020 to support her research in the region and contribute her expertise in ecosystem services, modeling, urban resilience, and also the science policy linkages. Now, floor is yours. You will give us a real example, the practical project in Melaka, right, Malaysia.
Thank you very much. All right, great. Thank you very much for the introduction. Pleasure to be here, and literally here at the lectern, because I was freezing to death at my seat over there, which is always ironic for this conference. I'm going to share what I call the ins and outs of heat stress monitoring through lessons learned from a project that we started about a year ago in Melaka as part of the Resilience for Communities program. So let me start with a very brief introduction to the program. Resilience for Communities was launched by the Resilient Cities Network, funded by the Zurich Foundation. And essentially the goal is to make all the big thinking and ideas around resilience more operational on the ground. So they're working with 4 cities in this particular program, including Melaka. And the focus is on flood and urban heat. When they approached us, they had already some expertise on flood risk, but they were looking for expertise on urban heat mitigation, which was actually quite topical, because the lab I lead, called the Resilient and Inclusive Cities Lab, is essentially looking at increasing the evidence based on the role of nature-based solutions for urban resilience, and really has a strong focus on action research. So we love it when partners and real people on the ground actually approach us to help us learn from what the challenges are, and also contribute our expertise on nature-based solutions. So that's for the background to the program and the project. I know it's the end of the day, and I don't know if you remember yesterday, Stefano said that we should have only one simple message. I have 2 key messages for you guys, because I have faith in you. So the 2 messages that I'd like to bring across for this final presentation is that we have enough data to act on urban heat mitigation, and especially in the context of nature-based solutions. I put here 28 kilograms, so I'm always saying that there's tons of evidence available. Technically, 28 kilograms, this is what was assessed as the weight of all the AR IPCC reports for the latest assessment report. So 28 kilograms, which is quite a lot of paper and lots of evidence on where essentially cities, in that case, should start when addressing climate and taking action towards climate mitigation and adaptation. So first message, we have enough data to start to act. There's no reason to wait. Second message, and this is the researcher and academic speaking, we do need more data. I think the other previous speakers have made that point as well. We do need more data to fine-tune some of the actions and also reflect on our action, learning from what we're doing to make sure that we can adaptively manage our solutions. So let me give you a few examples on this particular project. First, I think most of you would know, we have talked to Prof. Winston yesterday, mentioned nature-based solutions or green infrastructure as part of the key adaptation solutions. So I think they don't need a ton of introduction, but just to make sure we're on the same page, nature-based solutions are actions to restore, protect, or sustainably manage natural ecosystems or semi-natural ecosystems in cities. And they do 2 things. They benefit biodiversity and they benefit people. So the great things about these so-called win-win solutions is that they do provide a suite of benefits: air purification to a minor extent, flood risk mitigation for sure, carbon sequestration, mental health, and also urban heat mitigation. So this is why they are, and all these examples in Singapore illustrate how these types of solutions are already part of our environment. So we know, again, there are tons of things we do know, and we do know that these nature-based solutions work for heat mitigation. We know that through evaporation, through shading, vegetation, the point was made again by the previous speaker, vegetation does help reduce the temperature in urban environment. What we don't fully understand, and this is like the gap that we try to meet in a lot of our action research projects, how good is good? So we do know that lots of these solutions work, but in a very specific neighborhood, in a very specific country with all the uniqueness of the place, we don't know if it's half a degree, 1 degree, and I challenge most people, even if you have the most sophisticated model and sensor network, it's still a very challenging answer to give at a finer level. So that's one thing. Also, and lots of speakers have talked about it already over the past 2 days, differentiated exposure. So who is worse off? We do have data for cities at different scales, but we need to better understand for different types of communities, different types of housing, what is the actual exposure of communities and how vulnerable they are to future and current heat. So of course, again, just making the point that I'm not the only one saying this. IPCC reports, IPBES reports, the biodiversity equivalent for in terms of international consensus. All of these reports would tell you that yes, there is lots of evidence, but there are also gaps. And here I highlighted the urban heat island, as well as ecosystem base, where you see that there's low to medium evidence in some of these cities in Southeast Asia. All right, so that's for the background. We can now virtually travel to Melaka. Beautiful city, I'm sure many of you in the room have visited Melaka, World Heritage City, beautiful riverfront. It's also a very, very hot city. Maybe let's do a little bit of engagement. Who has been to Melaka in the room? Who has suffered from heat in Melaka? Yes, and I see Emma, my wonderful colleague working on the project, and I know she's the one, I think, on the picture, suffering from the heat in Melaka. So yes, a good reason to engage there. Also, if you're looking for field work, it's always a bonus if there's delicious food where you do your field work. So this does not hurt, and this is definitely a bonus. So what are the aims of the project? Quantifying heat exposure in Melaka. So when we started these conversations with the Resilient Cities Network, we identified these goals: quantifying heat exposure, identifying spatially these priority areas that may need additional attention, and then provide decision makers with relevant information. So we divided the project into 2 phases. First one is essentially desktop analysis. So we didn't even need to go to Melaka and try the delicious food. We could do this from Singapore with some tools and models that I'll introduce in a minute. And then the second phase was delving a bit more into these nuances, these things that we don't know when we start a project. So for the phase 1, we used 2 tools to do this desktop analysis. The first one is remote sensing. So this is something that technology has lots of advances. We had some wonderful examples of this in previous presentations. With Google Earth Engine, most, I'm not saying that it's easy, but it's made much easier than what it used to be. And so we can have land surface temperature mapping, such as in this picture, to already understand some information about heat. Land surface temperature is temperature, but it's not the temperature that we feel and that we experience in the city, so it has also much higher values. That is not what we actually respond to. So it's useful, but not so useful for prioritization. So this is why we used a second tool that we have further developed and tested here in Singapore. This is a tool that I helped to develop in my youth called INVEST. And the goal is to estimate benefits from urban vegetation. And in that case, heat mitigation by urban vegetation. So as part of the Cooling Singapore 2.0 project, which I'm a co-PI on, we have further developed and tested this geospatial model to make sure that even if it's a simpler approach to the very sophisticated models that are available in Singapore, does it give a reasonable first estimate of temperature? Answer is yes. So great, we can feel comfortable using it for exploratory analysis. So we use that in Melaka with no additional calibration, so essentially the same parameters as in Singapore. And this allowed us to provide this type of information for the funders and for the city, essentially looking at which of the priority communities that they had identified were exposed to heat the most. Also, you can see on this graph here, correlation between tree cover and urban heat island intensity, strong correlation. Again, things we knew before, trees do help reduce temperature. So great, first report, funders are happy, partners are happy, we think. And so this motivated us to go to the second phase of microclimate monitoring with the idea of better understanding, well, validating these models from phase one, and then getting into these more nuanced data of, are there some households worse off than others? Temperature, variation outdoors, etc. Also from a research standpoint, testing low-cost sensors, which is interesting in itself as to test the tool itself for other projects. So we focus on two communities that were identified by the city. You can see very different types of housing, more traditional type of housing on stilts, and blocks of units here in affordable housing in Pantai Peringgit. So we started the second phase with supporting the community engagement that RCT was leading, presenting the work, what the sensors could do. We had some very nice fans, also not as fancy as the GHIN fans, but we were very proud of our fans still. And essentially recruiting volunteers for the sensor installation. Fast forward, sensor installation. Again, credit to the wonderful team for this deployment, indoor, outdoor. I'm going to move on. And so these are the very preliminary results just from a few weeks of data that we have collected. So you can see that the more traditional housing, which is in blue here, actually tends to be much higher during the day, but also cools down much more during the night. So that's interesting, as opposed to the much more insulated, because all the blocks are kind of insulated each other from the heat. So much more constant over the day. You can also see that the temperatures do get quite high, and here we have WBT, wet bulb temperature, as well, because we only have temperature and humidity as data sets. So we're starting to get some insights into these different types of housings. From outdoor sensors, preliminary results also comparing the downtown very built up in pink to the parks in green. Guess what? We are seeing that the parks are cooler. So again, things that we knew before, back to my point about there are lots of things that we knew, even from the desktop modeling. This is what we had predicted from simple models. So this is the extent of the data that we have so far on the project. Just a few points to share on the next steps and some reflections. So first, I just presented these raw data. We do need to take the next steps in terms of interpreting these data together with the social survey data that was conducted by our cities, our partners, to try and see what it means in terms of exposure, vulnerability, potential solutions. So this is the next step. In terms of action research on urban heat mitigation, just a few thoughts. So yes, we have enough data to get started, but it's still very useful to have local data to help build evidence, engage, and really get buy-in from the city. And our partners in Melaka are really wonderful and super proactive. But it does help, build capacity, get them to understand what is good data, how to use them for their own purposes. Similarly, I mentioned the INVEST model that we use. Not the most sophisticated model, but in the same line of thought of open science and empowering our partners with basic GIS skills to be able to run these models and use them for urban planning. So that's really the goal here, as well as possibly some more sophisticated science projects similar to what we're doing in Singapore, validating the model to further improve its performance. And so this is my last slide. This is not rocket science by all means, a relatively simple projects in 2 phases. But I think the idea of using open source data, low-cost sensors, the approach and the workflow that we develop may have potential for other cities. So I'd be very happy to, some of this is already available, and we'll publish the rest in the next few months. But very happy to talk about how this could be deployed also for many other cities that, as we discussed over the past 2 days, may be interested in similar data and similar projects. So do reach out if you're interested in this type of project. I'll just go back to my 2 key messages in case you have forgotten them at the end of the day. We have enough data to act, so absolutely no excuse to not start projects. But also it is useful and also to tap into academia where there are resources, especially in Singapore, to collect more data and with the 2 goals of producing information, but also engaging with partners in a more meaningful way. With that, I'll stop here. Thanks for your attention and happy to take any questions.
May I invite our session speakers come from the floor and stay here. Thank you. Okay, for the audience, you're welcome to submit your questions to the Pigeonhole. Now we already received a few questions. The highest question is about aside to design for thermal comfort, how can developers city enforce building codes that promote heat resilience in new constructions? Maybe Mr. Lai, you can answer the question.
Can I take yours? Well, if aside to design for thermal comfort, how can developers enforce building codes, promote heat resilience? Well, developers will not do it voluntarily, let me tell you. It has to be legislated and it has to be enforced. And there are two levels or 3 levels of legislation. First is that when the building plans come for approval to a municipality, at that point, sizing, orientation, shading, insulation, all need to be mentioned specifically. Simple rules to be followed, not very elaborate calculations required. These could be prescriptive and it's quite easily done. Once you have that, one hurdle is over. Everybody is on the same playing field. If it means a little bit extra cost, everybody incurs that little bit extra cost. But it's not more than 5% extra cost. The rest of it is just design. Second is, during construction, there needs to be inspection, especially if it comes to roof insulation and shading systems and ventilation systems. Third is when the building is completed, right, there does need to be a review before an occupancy certificate is granted. So these are the regimens that have to be followed, and developers will jolly well fall in line.
Thank you. As far as I know, Dr. Yuan Chao also have this kind of collaboration with URA, HDB. Maybe you can also share some information and your experience from Singapore about this question. Yeah.
I would like to say that, okay, to enforce, maybe not enforce, to encourage them or to motivate them to have more evidence-based building code. Actually, we should provide a more accurate scientific understandings on how the buildings will affect the microclimate. Then they will be more motivated and encouraged to enforce the building code. Yeah.
Thank you. Okay, let's move to the next question. Oh, yeah, sure, please.
Just add, I think from an Indonesia perspective, where we've done some research on new towns. So essentially, what we call new towns are built from scratch towns by private developers. We found that they are actually quite keen from a marketing angle to provide green infrastructure and cool design. So I think there could be also an angle from their perspective is if they can market the cooler design and maybe lower air conditioning consumption, this is something that they may incentivize them to actually build in a cooler way.
Yeah, thank you. Actually, we have a next question, also the highest votes, which is how can communities be engaged in the process of developing heat resilience urban strategies? Maybe Professor Hamel can also answer the question.
Thank you. How can communities be engaged in the process of developing heat resilience? Well, I can give my slides again. I think this is one example of how it has been done in Melaka. There were also some excellent examples from other presentations today that I listened to. So definitely people are doing it, and when I say people, meaning the cities themselves as well as the Red Cross that is here in good numbers at the forum and sharing a lot of the experience that they are gaining throughout the region. So I would say that some strategies that have been used in Melaka are about community events. The engagement that we've done is essentially incentivizing people to join with some activities, some fans, some good food that was also provided as a way for them to join with families sometimes and getting them interested in the projects, especially when there is this science component where we were asking for volunteers to get these indoor sensors into their homes. So this is part of, I guess, the action of the project.
Yeah, thank you.
In the research work that we did for housing in India, we did go to a number of existing examples of urban housing, met with families and engaged with them. The families themselves helped in monitoring the internal and outdoor conditions, and they learned directly from that monitoring process exactly what's going on. And what we did find was it was the women and the girls who were most interested in health and well-being. And they would be the people who would, within their families and within their communities, develop a resilience attitude rather than develop fear of climate change, learn how to cope with it. And we thought that they would be the center of, let's say, a cultural movement that understands climate change, women in affordable housing societies.
I'll just quickly add, although I'm not really specialized into social science, but it's very important to engage with the communities like longitudinally for them to feel the perceivable benefits of whatever heat resilience or adaptation plans. For example, like the HDB project that we participated in, part of the research scope requested by our authority is to really to conduct such survey, right? Like along with data collection. So because climate adaptation is a very professional thing, right? It's really, many times it's just understood as it's government's responsibility, it's infrastructure investment, it's professional equipment or something provided by the government, but we have to really engage with the citizens and let them let them share what they feel actually. And that's part of the merit of the thermal comfort design in the buildings. I think a huge part is really personal perceptions, and which is not yet captured in what we do as a professional technology and instrumentation provider, and that is a gap to be addressed as well.
Thank you. As far as I know from the URA Singapore government and also the Hong Kong Housing Authority, when they develop such kind of large public housing rental estates, very often they will conduct this kind of community engagements at the beginning when the government officials to propose their design proposals in the construction process, even post this kind of design stage. So I think that is quite popular way to get a feedback from the residents and also from the neighborhood communities. Okay, now we have a question to Professor Yuan Chao. In what way can household and individuals make use of the microclimate digital platform to better address heat? It seems your video is very powerful and people would like to involve that, not only the students. Thank you.
I would like to say that different stakeholders and actually can apply different ways to use the information to help the different vulnerable groups. So the public, of course, is one of the most important stakeholders. So for example, they can access the information and they can make the decision like, okay, so which neighborhood they should choose regarding the microclimate quality and to live at. And they can do the very basic assessment. Okay, so what's the microclimate, and if the natural ventilation performance is good, then maybe they can open the window more often to enjoy the natural ventilation and use the less AC. Sometimes now we are trying to integrate the real-time measurement data into the digital platform. So you will be able to know today or tomorrow whether the air temperature will be higher or not. So that you can follow up the necessary actions like drinking more waters and this kind of things. You can either reduce the outdoor activity times or extend the outdoor activity times. Yeah, so a lot of decisions can be made based on the climate informations.
Thank you. Okay, there's another question talking about natural-based solutions. I think somehow 3 out of the 4 speakers, their presentation somehow touched this kind of topic. So the question is, are natural-based solutions slower and less cost-effective for heat adaptation? What consideration must be taken for NBS, natural-based solutions, to balance between the climate adaptation and mitigation? Yeah, please.
Well, we've seen a lot of simulation about nature-based solutions being useful at a city scale. We are seeing that. But at a, let's say, a neighborhood scale, at a scale of a number of buildings put together, the visibility of the sky to the face of the buildings, apart from its roof, is a very important aspect of nature-based solutions, because if you leave enough space between buildings where blue and green infrastructure can be woven between buildings, that's the way of dealing with urban heat island, as well as reducing the microclimatic impacts as much as possible thanks to evapotranspiration. So integrating, and there needs to be some design guidelines for each climatic situation to suggest what is a right optimal balance for getting the best out of it.
Perhaps I'll add to this the nature-based solution community, and I guess I'm part of it, has done a wonderful job at making this term stick, which is great, but we're also talking about very different things. So in urban environments, a green roof is a nature-based solution, an urban forest is a nature-based solution, a lawn is a nature-based solution. And these 3 things have very different impacts in terms of reducing temperatures in cities. So it's important to remember this, that it's definitely not one size fits all, and that they have different co-benefits as well. So that's one point, and I think part of this answer, of the answer to the question that I would give is, yes, nature-based solutions can help reduce urban heat mitigation, urban heat in cities, absolutely, but they also will not do much during extreme heat events, and so we do need, and this is the whole theory of urban resilience, we need multiple solutions and also some air conditioning when we can afford it for the resilience centers, for example, in the communities that would effectively, during heat waves, bring the temperatures down much more than tree planting, for example. So it is a combination of these solutions that will help adapt to the changing climate.
Yeah, I just want to share one very quick finding from our HDB project. Also, the rooftop greening actually cools down the building surface much more effectively compared to cool pen because simply of the moisture it holds and the evapotranspiration project, the effect of that. But then, of course, in how to scale it up, I think that's a key question here, and what is the cost? So I think that's something really is very unique to Singapore's case, that we are leveraging so much on green infrastructure. Yeah.
Thank you. Given the limited time, so maybe we have the last question for this session. This question for Indian cities. While suggesting horizontal urban development over the vertical for Indian cities, how can the travel distance and urban sprawl can be addressed, considering the car-reliant behavior of the people?
Yeah, I think there's a real misunderstanding about what we call horizontal sprawl. We're talking about compact cities which are produced by going 4, 5, 6 stories high, generally, with space between buildings, as we were showing. This compaction gives you, if you account for the space required for social infrastructure, schools, hospitals, playgrounds, etc., markets, in addition to homes, just vertical high-rise in one space does not actually save much more land. We've done studies on that, finding that 4 to 6 story high at the city, at the gross density level or gross floor area ratio level, works out to be the optimal solution for compact cities with low mobility costs. So it's not urban sprawl, it is dense city, but high density, low rise. That's the solution.
Yeah, so actually I totally agree with you, and we certainly should say no to the urban spreading. Okay, and the high density actually is very useful to improve the land use efficiency and the energy efficiency. But we should not go too extreme, because the density also causes issues like the UHI and a lot of standard areas, very poor natural ventilations. So I think Singapore, the density is quite just right. The Hong Kong, maybe the density is too high, too extreme. Yeah.
Thank you. Okay, now we are approaching the end of this session. May I invite each of the speakers, maybe give one sentence, like a take-home message. Okay, wrap up our session. Thank you.
Let's start from there.
Yeah, maybe we start from the Professor Hamel.
Thank you.
Thank you.
Yeah, I already had my 2 messages, thank you. I think I'm trying to find commonalities in everything that we shared, which is not easy. It was a very diverse set of speakers, but definitely some commonalities in the simulation and monitoring in these 3 presentations, as well as some, I think the key message also coming from India, Prof. Lall, or Dr. Lall, in terms of building codes, and that we do know the solutions that work, and we just need to implement them. So maybe just do it will be my last message.
Thank you. Next one.
there are a lot of things can be done, and let's carry on. Yeah, thanks.
Yeah, I just want to share my deep appreciation of our scientists and our architects, because they are the trailblazers and change makers, whereas I pursue the wrong education. I'm an engineer, so I have to be very practical and grounded. And to me, it's a nice forum for me to learn what's new and what kind of knowledge is really ready for the market and can be spread around, and we can also what is appreciated and what is affordable. Yeah, that's our role.
I'm just trying to connect two supposedly disparate ends. On the one hand, I think that the visualization of seeing the entire island of Singapore, and you see these vertical bars rising and changing colors, is something which is a strong communication device for urban planners and city planners and architects to understand the impact of urbanization and anthropogenic factors in the heat of the city. So I think everybody should use that tool to talk to their communities. On the other hand, I didn't mention this earlier, people who are going to be living in homes, especially affordable housing, need to know through a strong communication strategy what they deserve, that they deserve good design. And they should know that this is achievable at practically no extra cost. And I think when the demand from an informed public rises, the government as well as the developers begin to respond to it. Okay,
let me also share my thoughts. I think our panel, including me, we have very interesting combination. Four of us with architectural planning background, one with environmental engineering, and now we have the industry people which can provide equipment, right? And also we have professors which have a powerful digital information platform. So if you want to do something, you have the data, you have the equipment. Now we have an architect who can help you to do a good design. And then Professor Hamel also can help you to do the community engagement. So come to us and we help you. Thank you so much. Let's end today's session. Thank you for your support and participation.